Hi, welcome back. In this lecture, I want to introduce to you the cProfile module that we're going to use to profile our application. And most importantly, we're going to use to understand which function take most of the time of our code. By the end of this lecture, we will be able to obtain profiling information about the most used function in the code with the cProfile Python tool. We'll be able to analyze the cProfile output and statistics and understand the impact of different functions on the overall application timing. Finally, we will be able to visualize the results of our performance measurements using the SnakeVis tool. The tool that I'm going to introduce to you today is the cProfile tool. cProfile is a built-in profiling tool in the standard library. What it does? Well, it hookups in a Python interpreter in CPython to measure the time taken to run every function that the Python interpreter sees. Profile without the C is the original and slower pure Python profiler. What we're going to use is the cProfile. cProfile has the same interface of profile, but is written in C for a lower overhead. So we want to use a profiler that is more performant than the original Python profile tool. If you are curious about the history of these profiling tools within Python, it's nice to check the email and to the mailing list. See here the link to include the cProfile in the standard library. So here I have a snapshot of this email. It's quite interesting. As you can see, the beginning is quite interesting. Said the current Python profiler situation is a mess, so we need to act and fix it. And therefore, the cProfile came up, and cProfile is the tool that we are going to look at now. So let's get back, to the previous lecture when I talk about, why we do profiling and how to do profiling critically. So whenever we do profiling, it's important to make some hypothesis. So a good practice when profiling is to generate a hypothesis about the speed of parts of our code before actually profiling. We are basically using profiling information to validate our hypothesis or not validate or dismiss our hypothesis. In this case, so we know the code is going to be our Julia set code that I introduced in the previous lecture. Thinking back about that code, we can hypothesize that the calculate serial pure Python function that I posted here on this slide is the slowest part of the code. Why is that? Well, it contains quite a lot of differencing here. Is doing quite calculation heavy part here during these loops here. So this is for the pixels, and this is basically to check the escape condition. So we have this operation here, and then also we have for each pixel and for each iteration, for each pixel, we need to check the absolute values of the complex number z. So it's safe to make this hypothesis that this is the function that is taking most of the time, because it takes most of the arithmetics, differencing, and has the abs function. Here we can use the cProfile module to run the code against it. The output of the cProfile is kind of synthetic and Spartan, but it's going to help us to figure out where we want to analyze further. And in the next lecture, we will go deeper and deeper on this. So how are we going to run the profiler? Well, we don't really need to do any change in our original code. So our original code is called Julia set.py, and this is the code to calculate the Julia set. So we call it Python go Julia set. We are going to introduce two flags before calling our Julia set.py. And one is -m cProfile. So we're going to activate our cProfile. And then we provide an extra flag. This is going to feed in the cProfile, -s cumulative. So the -m cProfile is to use the cProfiler, and the -f's cumulative flags tells cProfile to sort the results of the different execution time of our function by the cumulative time spent inside each function. So we want to have the output from the most important from the function that takes most of the time to the one to the less. So this gives a view into the slowest part of the section of the code, and cProfile output is written to screen directly our print results. So we don't need to do, we just run it. Here I have an example from the command line running on my laptop. I call Python, the code is juliaset.py, and I give this extra flag. I augment it with the profile information, and then I want the information in the cumulative time. So these are the output that we would get without the profiler, and then we get in basically the more additional information about the profiling. So if you use Python minus cProfile, is going to print out after the execution of our code the profile information that we obtain from cProfile. So now let's look at more into detail this output from cProfile and try to analyze it. Okay, so the first information that we have is we see that entry point here is our main function in the juliaset.py, and this is on line 1. Here we see that is taking 5.2 seconds to run. This is just basically the main function to calculate the pure Python calculation. The number of calls that we have, our main is basically just one, as expected. So this end calls is basically tell us how many times this function is executed. In the case of the main, only one. We move on the analysis of our cProfile output. Inside the calc pure Python, that is this part here, we saw that the call to the serial pure Python here is taking 4.9 seconds. Also, we saw that this function here only called once. We can, by taking the difference between this timing here, we can derive that approximately 0.3 seconds is spent on lines of code inside calc pure Python. So a separate to calling the CPU intensive called serial pure Python function. However, we cannot really derive which lines takes the time inside the function using the profile. In the next lecture, we are going to see a different tool to have a more fine-grained view about the profiling line per line. So let's move on the analysis of our output from cProfile. Inside the serial pure Python, the time spent on lines of code without ever calling other function is 3.9 seconds. We saw that within this, so this is the 3.9 seconds, and then we start analyzing this function here. We saw that the function apps that we are going to have here makes 34 million calls. That's quite a big number. We saw that by analyzing the n calls here. We saw that this is called 34 million, and approximately it takes 0.97 seconds, right? So almost 1 second. So it does not really takes my time, but the amount of time is really a lot of time. If we want to dive into more analysis on this, we saw that the per call cost is negligible. So if you see that the cost for one apps calculation is negligible, is equal to 0, but the total number of times is 34 million, as we saw before, and the total time is roughly 1 second. So if this is the total time is 5 seconds, we see that basically 1 second is dedicated just to calculate the absolute function. An interesting part of this, especially for the Julia set is that we cannot predict in advance how many calls would be made to the apps. Remember that some pixel will get out from iteration quite quickly, otherwise we'll keep iterating and they will reach max iteration. So there is this issue that we call load balancing issue, because some pixel they are going to do a lot of work, some pixel are going to do less works. Moving on to the next important function that we're going to see here is the append function. That is the function that we do at the beginning when we create a list with all the coordinates of our pixel, formulated as a complex number. We saw again here the time here is negligible, but the cumulative time is a fraction of a second. We saw that we create 2 million of items, right? And this occurs on CalcPure Python, where we created a list during the setup phase. The ZC and CS list will be 1000 by 1000 items, and then we are going to do two calls, right? So we're going to have just 2 million calls from this, and these are built from a list of 1000 by 1000 coordinate. So we are going to have in total 2,000,000 calls to append function to create our list. Finally, the last line of the profile information is about ls proof. We can happily disregard. It's just historical. As you probably remember from the first slide, when I was quickly commenting the email, that email is really about lsprof. That is the original name of the tool that evolved then into cProfile, and this can be ignored. So we saw that if we just call from the command line Python -m cProfile, it directly output to the standard output to the screen. One thing we can actually do is redirect the output to a -o profile stat file. So we do as before. What we are going to do is going to, instead of having on the screen, just after the execution of our program, we're going to redirect on a file. So we run our code, juliaset.py. We are using cProfile, and then we create a file called profile.stats. So that's the first step. The second step will be actually to see what are the results of our profile information. For doing that, we are using the Python shell. So we start Python on the command line. We're going to do to import first pstats. That is the module that we need to load it and allow us to analyze this information from the profiler. So we import pstats first. Then we create p using pstats.stats, and then we provide the name of the file with our profiling information. So we loaded first the profiling information from the file, and we store it in p. We sorted the information depending on the cumulative time, so from the one that takes most of the time to the last. And then finally, we are going to print the stats. As you can see here, we obtain basically the same information that we obtained before by just profiling and printing to the standard output. So far, we analyzed the information looking at this sort of table that is sorted from the function that takes most of the time in cumulative time to the one to the list. It's often very useful to use visualization tools, especially when we do not very well the code and we want to have a very quick understanding how the code works and what are the most computation intensive part of the code, or where our code is taking a lot of time. So SnakeVis is a visualizer tool that draws the output of the cProfile. So it takes as an input that profile file that we generated in the previous slides, and then it visualizes. So it visualizes as a diagram in which larger boxes of areas of code takes longer to run. As I told you, SnakeFix is very useful to get a high-level understanding of a cProfile statistics file. This is particularly good when we are investigating a new project, a new code that we don't know well, and we want to have a quick understanding of the different functions of the code. The diagram is helping us to visualize the CPU usage behavior of the system, particularly what are the functions that take most of the time. To install SnakeFix, we need to use pip install SnakeFix. You will need to install it on your system. You go to the command line pip install SnakeFix. To run it, we need to have our profile file available from running this command line. So we have our code. Remember here -o profile.stats. We provide it here to SnakeFix, provide stat. We need to tell Python that we're going to use this SnakeFix, and then do not forget to put at the end -- server. We will, when run, will give a link that we can open using a web browser to visualize interactively the information about the profiling information. When you run this, you will get a link, and when you take that link, you will open up on a web browser, the one that you prefer. If you do that, you will see a web page that is very similar to the following. So we have two parts on this SnakeFix report. The first one is visual information about how the code is running. As I told you, we have rectangles to tell how much time is taking the call. So in this case, we have the blue ones that are basically the main function. Then here our function, and you see that the calculate this here pure Python, that is this cycle for each pixel, and for which we calculate the escape condition, is roughly taking 90%. Just judging by eyes, you see that this is roughly 90% of the old codes. If you open your browser, also you can interact. So this, if you go with your cursor here, it will open up some more information. It's also allowed to choose between different graphical visualization and also how to go depth in the stack. So together with this nice visual representation of our profile information, we also provide a classical table view of our profiling information. This is my last slide. So to summarize, cProfile is a built-in Python profiler to measure the time taken to run every function in our code. cProfile is ideal to find the most computationally intensive parts of our code. cProfile is typically called from the command line with -m cProfile, and can either print to the standard output or to a file with all the statistics. If we go with this second option to write output file with the statistics, we can visualize the output file with the SnakeFix. That is going to give us a graphical view of all the statistic information. Talk to you soon.